Hello, everybody. My name is Behnam Mobaraki. I'm professor in the Department of Graphic Engineering and Design at Polytechnic University of Catalonia, UPC in Barcelona, in Spain. So in this presentation, I'm going to present a part of my research, which is focused on the thermal bridge performance in Mediterranean buildings, a finite element analysis of envelope weaknesses. So as can be seen in the presentation, this job has been conducted by myself, Professor Abdullah Mubaraki, and Professor Mojdeni Kufam from the Department of Architecture at Cyprus International University in Northern Cyprus. Engineer Mohammad Bagher Ahmadi from Design Construction Company, Ariska Iranian in Tehran, in Iran. And finally, Professor Frederic Villamarti. So in this presentation, first of all, I'm gonna give a general picture about thermal bridging buildings. Then in the next step, I'm gonna present thermal monitoring system, Internet of Things, hyper efficient Arduino transmittance meter. In the third step, I'm gonna present test description and finally result of finite element analysis. So, as can be seen in the screen, a thermal bridge is a localized area in the building envelope where heat flows more easily due to the material differences, geometric discontinuations, or interruption in insulation. So as can be seen in the image, at the junction, such as wall floor connections, heat transfer becomes multidirectional and concentrated, leading to a higher heat loss compared to the surrounding areas. So let's say this results in a reduced thermal performance, lower interior surface temperature, and finally potential risk of condensation and mold growth. This study addresses thermal bridges, let's say these gaps, by employing finite element method based digital model to analyze thermal bridge performance in a representative building envelope located in Barcelona. So in addition, in situ thermal monitoring was conducted in a residential building to investigate thermal bridge performance, or let's say thermal bridge behavior, and finally the collected data were used as an input of the FEM model. So in this research focuses, let's say we have focused on quantifying heat flux, temperature distribution, and linear thermal transmittance across key envelopes junctions. In this way, we could study the junction, or let's say thermal bridge weaknesses in a residential building. So the numerical analysis was performed using three-dimensional finite element method, representing a section of the facade wall, including critical wall-to-wall junction. The geometry was discretized using unstructured triangular elements, which are well situated for capturing complex geometrical features and the material interfaces within multi-layer assemblies. At the end, to accurately represent heat transfer phenomena, particularly, let's say, in the region with the high thermal gradients, a non-uniform mesh was adopted. The analyzed wall was a typical multi-layer facade system commonly found in Mediterranean residential building. Total wall thicknesses approximately was around 32 centimeters and consist of the following layers, let's say external cement render, hollow clay brick, air cavity, lightweight concrete, block internal gypsum, plaster. So on the left side, the 3D finite element simulation illustrates a thermal bridge at the structural junctions where heat flows concentrates along the connection between elements. The color gradient shows temperature distribution with warmer zones indicating higher heat transfer, while let's say cooler areas reflect lower temperature. The localized, let's say, intensification along edges and interface highlights how geometric discontinuation creates preferential heat path, reducing the overall thermal performance of the structure. And on the right side, the finite element simulation shows thermal breach where heat flows concentrates at the wall slab junction. And finally, this gap, which is a summary of all the results obtained in the finite element analysis, we can see how the U value, or let's say transmittance parameter, decreases rapidly near the junction, or better to say that at the thermal breach zone, and then stabilizes at the distance increases. So let's say the higher U values close to the edges indicate a greater heat loss due to the thermal breach. So this comparison between the two curves finally can show us how different configuration or condition influences heat transfer behavior. Many thanks for your attention. Please feel free to write me if you have any question.